All right, greetings, Statesman. We are live now. This is one of our first live streams, first one that we're doing here on a Sunday. So this is lesson 1.2. I need to do an audio test, so just making sure that that is working. Give me just a moment. Want to make sure that you guys can hear me. Um, awesome. Looks like that's working fine. So the audio is good. Just making sure that the microphone is all tested out. And so here we go. So we have lesson 1.2, which is measuring and constructing line segments. So I'm going to jump right into the lesson. Some of the school materials that you should have acquired by this time. You should have a compass and you should have, of course, a calculator. Compass is going to be an important thing for you guys to bring into class because one of the things that's going to come up has to do with how to construct a segment, which we're going to get into these constructions actually in class right away. So make sure you have your compass for when you come to class. But in the meantime, actually, we're going to use it today on this lesson. Um, you guys won't be able to see me use a compass as I'm working right now. All right. It's unfortunate because I'm not live streaming a video of my hand, but in class I'll be able to demonstrate this on a projector using for the video beam in a document camera. So what we have right here is we have a line. Now we talked about this in our first lesson. So this is signifies, right? We have these arrows that we write at the end of it that signify that it extends infinitely. What's great is my software here actually can create these lines. We're going to make sure to do some automatic shapes, but moreover, I can actually have it just do a line. And when I use that, right, or write that, it'll have on it the little arrows at each end, which means that it extends infinitely in each direction. So make sure that I'm going to change my colors here. Um, just kind of working with. Infinitely. Oh, one of the things actually I think is a feature here is to get this thing to um, within my text. See automatic shapes. Nope. Try touch shapes. Snap to grid. That's good. Oh, there used to be a conversion tool to make my um, writing a little bit clearer. That way it would actually change my handwriting here to text, but that's okay. We'll stop to do that, and I'll actually type some things out when it's a little bit longer. So anyway, this is going to mean it extends infinitely when you have this on each of the corners, so or at each of the ends of the line. So I'm going to take a line, and it's going to be line AB, but within line AB, I could actually just confine it to be this portion of it, which is the line segment AB. If I wanted to, and one of the things that our textbook is going to decipher right away is the matter of being congruent. So this notion of congruence. This is when we get into the second chapter, one of the things that's going to come up as we're doing proofs is first of all, we're going to have postulates and definitions. But one of the things that the textbook uses is something that's called the definition of congruence. We are not going to use that. I've gone back and forth over the years and have had a big turnaround about this notion. It's really important. It's a very different concept, something being equal versus being congruent. Congruence meaning that a segment or an angle has the same measurement, so it measures the same. Therefore, um, we can make it equal. Um, so it's not like they're interchangeable because there is a slight difference in the definition, but it's something in terms of converting our notation. I'm not going to pick you guys apart with it. It's just there's an old saying which is the juice isn't worth the squeeze. It's really not worth me beating you guys up over it, and I think it just causes confusion. So we're going to just worry about this. We're going to worry about when we do congruence, right? I want to know what this distance is between A and B. So what I'm going to do is I'm going to take my compass, okay? And my compass, I'm going to actually copy line segment AB, and I'm going to make point C, and I'm going to make CD. So what I'm going to do is I'm going to just put my compass where I'm going to put the needle right here on point A. And then I'm going to extend this thing over and the width of the compass, which we're going to call the radius. And I'm going to move that guy over. And I'm going to here with my compass, which I'm using, I'm just kind of holding up against my pen, and I'm going to make a little tick mark right here to get my point D. And that now I have something of equal length here, or it's the same measurement. So then here, when I go back, I'm going to trace this guy. Okay, I'm using a straight edge to trace it. Um, it's a little messy here. Um, And when I do that, of course, on each side of this, I have these points, which means this guy right here, this terminates, meaning that I have a finite, a definite ending to both sides of the segment. All right. And then now we have this notion of congruence where we have AB, which is congruent to CD. And this is how we do congruence. It is with this little guy right here. You guys see that? This little equal sign, and you see that squiggle on top. This means congruent. Oops. So what that signifies. So that's part of our notation. AB and CD are congruent, meaning that they have congruence means that they have the as I said before, that these guys have the same measure. All right? That's all it means. So AB has the same measure as CD. And again, I'm not going to really haunt you guys with, oh, you said equal when it really was congruent. You said congruent when it really was equal. In the end, I'm comfortable, and I know this is where, if there's anybody, the fly on the wall, if there's a mathematician who happens to follow this, and wants to have that discussion with me, wants to have that argument with me, I welcome it. As it is an important concept. It is in terms of differentiation, but it's okay for you guys to understand as we're starting off on this that that's really what we're going for. Is that when we're saying that AB is congruent to CD, it's pretty much the same thing as us saying equal. Pretty much, it's not the exact same thing. It's pretty much the same thing. Okay, so let's move on. Got lots to cover. I'm going to want to make this video actually a little bit shorter than the previous lecture that exists right now for this that some students may have already viewed and taken notes on. All right, so we're going to make a little coordinate plane here. Remember, when you make a coordinate plane, we have two axes. And we're going to try to establish congruence. And remember, we have our vertical axis, which is the y-axis. And we have the horizontal axis, which is the x-axis. So I'm going to give you guys a series of coordinates. And we're going to see if we have two congruent segments based upon, we have AB congruent to CD. So I'm going to give you guys coordinates for A, B, C, and D right over here. So A has the coordinate -2, 4. B has the coordinate 3, 4. C has the coordinate 0, 2. And D has the coordinate 0, -2. So, one of the things to look at with this is, do we have any congruence with AB to CD? Now, gentlemen, it means that they'd have the same measurement, and we don't really have a way right now to deductively prove, and that's what we're really going to get to in the lesson after this. Because right now this is gonna be inductive. We're gonna eyeball it and just and use a counting principle, and that's fine for now. But we're gonna see where once we get past what's vertical and horizontal on the coordinate plane, to differentiate size and distance is going to be really challenging. Once we get out of that, when you start to get a little bit askew. So let's graph these on the coordinate plane. Now remember, the coordinate plane operates alphabetically, that these coordinates are x, y. If I had there is a three-dimensional coordinate plane. We have a two-dimensional one right here because it has two axes. A third dimension that is a thing, and you can graph it. It would be the coordinate z, so which would be x comma y comma z. I'm not worried about that right now, guys. We're gonna keep it simple. Refer to the stuff that we did before. So here, this is fine for me. Is you guys can just give me two tick marks, -2, so it's left two, and then we're gonna go tick marks up 2, 3, 4, and I'm gonna plot my first point for point A, and then for point B, I'm gonna go 3 on x, 1, 2, 3, and then up 4 for y, and this is my point B. Okay. And then for C, I have 0, comma 2. So I'm going to be at the origin, right? This guy, 0, 0, right? The intersection of X and Y. And then I'm going to go up 2. So this is the coordinate C. And then I'm going to go down 2, right? 0 at the origin, and then down 1, 2, -2 for D. All right. So this one, I hope is apparent to you. We can use the counting principle. But if not, if nothing else, take your compass, spread it the width, and that's one we're going to see it. Now, if we this is where we get into some challenges. If we have our crummy writing, and we talked about creating perfect figures, it's really we can't do that, right? I can't really create exactly something, and this is where the compass is really flawed. In fact, your textbook. This is a funny little thing. Your textbook has this thing that has the ruler postulate. I hate this. This is not a thing mathematically. I will happily argue this with the writers of this textbook or any others. Gentlemen, this ruler postulate, circle and a line through it. We are anti-ruler postulate. Reminds me of a story. Real quick, my nephew, when he was in kindergarten, he's now in his 20s. When he was in kindergarten, he broke up with his first girlfriend by handing her a note that said, you plus me with a circle and a line through it, and he gave it to her. It's pretty brutal. It's pretty tough. But yeah, this is one of those things. The ruler postulate. I'm anti-ruler postulate. Can't do it. Don't do it, please. It's flawed. It's not a postulate. Rulers, like we talked about, the only perfect things we have are within the mind. And that's where we find, divinity and so forth, as Augustine relates that to this Platonic idea from the Republic. But nonetheless, guys, just don't do it. We go back to, again, we're going to eyeball this thing. Really, if we use our counting principle, the big thing is if you can measure it with your compass, it doesn't match up, right? This guy is 5 units, where this one right here is 4 units. Obviously, AB and CD are not the same, so it means that AB is not congruent because it does not have the same measurement as CD, is a different numerical value. Therefore, what we would do is we would write AB, and the symbol for not congruent is we take the equal sign and the squiggle on top, and we're going to slash through it. That means it's not congruent to CD. All right. Gentlemen, this is one of my favorite things as we start the semester. Baby's first postulate right here. It's really a sweet and exciting day. You guys are going to get your first one. You barely know what a postulate is. A postulate, as we get into the second chapter, we'll get to understand as being, a self-evident truth. Euclid and Elements, the text that we discussed in our first lesson, defines a number of postulates. He gets 5 postulates in and he has some problems. But here we go. We have the segment addition postulate, which states as follows: is that if B is between points A and C, then AB plus BC is equal to AC. All right. Let's illustrate what that looks like. So I'm going to enlarge that a little bit for you guys, so you don't have to squint. Illustrate. Ooh, goodness gracious. I don't have my software fixing my straight lines just yet. So I have A and C, but then I have B in between them, right? What it says is that we have AB, oops, write those things next to each other, and BC are going to be equal to AC. Now, what's something you guys should see is that above the AB and BC and AC, I don't have the little line segment above it. That is perfectly permissible from a notation standpoint. This is one that doesn't confuse students that much. I've found this over the years. There's almost I can't think of a single student in the thousands that I've now had who have ever been confused by that because it's less work, right? Usually the things that want to be in less work kids are buy into. So I just write 2 points down, minimum number I need. To say that it extends infinitely, I need the line above it with the arrows. But just write an AB. I got 2 points. Connect the two, you got your line segment. This is what I also refer to as our segment addition statement. This statement right here. Okay. A statement, gentlemen, is something we're going to find is something that is definitely true or definitely false. Um, it's not just an expression, which is just maybe one snippet. Like for example, AB plus BC would just be an expression, just something we would just say, right? But it has either some truth or it has truth or not, right? Not some truth. That's not a thing. It's just this is going to be definitely true, definitely false. AB plus BC is going to be equal to AC. When I have this entire thing written out, it's my segmentation statement. Please bear with me because that's going to come up again in the second chapter. It's pretty important. There is no segment subtraction. That's going to come up in one of our next examples. So let's go ahead and get to our final three examples real quick, guys. We have a line, we have X, we have Y, and we have Z. And for X on this guy, we have the following, is that we have XY, and I purposely drew it this way, where XY is equal to 14 and Y is equal to 27. This is something I want you guys to understand, which is you don't need to not worry about what it looks like. Worry about what it says. I know X, Y, and Y, Z look similar in length, but 27 is obviously to scale much larger than 14. I don't care. I need to find, this is your directions are going to be to find XZ. All right. Oh, it's right here, right? Got it. Cute. In order to do this problem, we need to do the first thing is just you need to make your segment addition statement, so which is going to be that XY plus YZ is going to be equal to XZ. You need to have a segment plus a neighboring segment is equal to an entire segment. Okay? Has to be done this way. Is no segment subtraction. All right? And then now we just substitute XY is really equal to 14. YZ is really equal to 27. And then XZ, we don't know yet. What we find out is that 14 plus 27, once we evaluate, is equal to 41, and that is our answer. You do not impress me by just skipping from XY plus YZ equals XZ and making this into XZ. That's not the purpose of this exercise. When you guys took Algebra 1, you were given, this is just a little sidebar, you were given the following, which is that X plus 2 is equal to 3. And you were asked to solve for X, and many of you guys were so excited to show that your teachers that you already know the answer is 1. Congratulations. So does everybody pretty much in the second grade and below, second grade, first grade, or second grade and above, right? Even many first graders and kindergartners understand what that answer is. They can just look at this. Cool. But the whole point is when we show you this in algebra, as algebra teachers, we want you to execute this inverse operation. It's a procedural thing because then this becomes a more complicated thing. We want to teach you how to utilize an inverse operation in that step, okay? That's kind of what I'm getting at right here, okay? So, get to our next problem here. Where we have B, C, D. And we have to remember what I said earlier. There is no segment subtraction. So this entire thing, BD, is equal to 25. And we have BC, which is equal to 19. And we need to find CD. All right. So remember, there is no segment subtraction. That is not a postulate that we're given.
We're just saying we have these two things next to each other. Clump them together, BC, CD. They share C, therefore BC plus CD is CD. So we're going to have to write that segment addition statement up. BC plus CD is equal to BD. Gentlemen, I need this. This is a mandatory step. Okay? I need this. Have to have it as you guys get into your problems in class. BC, we'll replace it. A substitute, and this guy is, you know what I'm going to do? I'm going to work in blue. There you go. Here we go. Plus, seed, I'm sorry, BC I was given. It was 19. I substitute CD. I don't have. BD, I was given that. It's 25. And then I go and I subtract to get CD by itself. Right? 19 and 19, that's going to cancel out. I have CD by itself. And then 25 minus 19, which is 6 whole units. Okay? Has to be done this way. We'll get into this in class. I'll be able to see which of you guys did not take notes and heard me pontificate about segment addition and the lack of segment subtraction in this world. Okay, here we go. Last one. We have PQR. Okay, so PQ, which is 8y plus 25. We have PR, this entire guy, which is 13y plus 25. And we need to solve for QI, find QR. Here we go. Step 1, write your segment addition statement. PQ plus QR equals PR. Second, substitute the values that we are given. PQ, we're given as 8y plus 25. QR is our unknown. PR, we're given as 13y plus 25. All right. And then we solve. We're going to subtract first. 8y. Please do these one step at a time. Algebraically, it's problematic if you start trying to combine steps. So first, do your variable addition with. Then 25 plus QR. Which is equal to 8y and 8y cancel. 13y minus 8y is 5y. Okay. And then I'm going to subtract 25. Both sides, 25 and 25 cancel. So QR is going to be equal to, actually cancels there too. It's just 5y. It's differentiated a little bit from my example in my notes from before. So that's all I got for you today, gentlemen. I will see you in class. Please reach out if you guys have any questions.